回避したんです。
まだ出てますよ。
はい、じゃあもう一回やります。横山智也、横山、どこ行っちゃったな。これ
9時になりますよ、そろそろ。
はい、中川先生も、兄さんに言ってください。
じゃあ、始めます。So, hello everyone. I'm Akiko Nakagawa Izumi from University of Tsukuba, Japan, and chairperson of session 3-1. Okay. So, at first, I asked the audience, so if you have questions during the presentations, so please write in chat using the Zoom, Zoom. So, because we can easily catch your question and we smoothly start the discussion part. Okay. So, let me introduce. So, first topic is alternative chemical pulping of non-wood and integration with biorefinery concept. So, speaker is Professor Ni from University of New Brunswick, Canada. So, Professor Ni, so could you share your presentation? And so could you on your camera? Are, なかったっけ?
Yeah. Yes, come.
Summer video. Yeah.
And could you turn on your camera? Okay. I checked.
Okay now. It should be.
So please start for your presentation.
Okay. Good evening, everybody, to those in Japan and Asia, and good morning to those in North America. Thank you very much, Professor Nakagawa. First, I would like to take this opportunity to thank the organizing committee, in particular Professor Oi from University of Tsukuba, in accommodating our contribution to this virtual conference. The title of my presentation is Alternative Chemical Pulping of Non-Wood and its Integration with Biorefinery Concept. In fact, it's a review paper which is just published in biofuels, byproducts, and biorefinery. I'd like to acknowledge my co-authors, Professor Johan and Dr. Rame. We are from the University of New Brunswick and Bangladesh Council of Scientific and Industrial Research. I will spend about 15 to 16 minutes for the presentation and leave about 5 minutes for questions. Okay. So now the pulping at the global stage is increasing, and China and India are two significant players. This map shows the large non-wood paper companies in China, and raw material includes straw, bagasse, reeds, and bamboos. In particular, in southwest regions of China, bamboo actually pulping as a raw material has been increasing in the last, I would say, 10 years or so. This is because bamboo in this region, in southwest region of China, is abundant, and also that species is growing very fast. Harvesting time is between 3 to 5 years, and it has favorable fiber characteristics. Of course, in terms of chemical compositions, in a lot of cases, bamboo are very similar to softwood and hardwood species. In terms of ash content, yes, they are higher compared to those in wood species. However, they are substantially lower compared to those in straws, like wheat straw or rice straw. So bamboo can be important fiber sources for pulp and paper, particularly to countries that are lacking in woody materials. In fact, China now is producing more than 2 million tons of bamboo pulp. And other countries, for example, India, also rely heavily on bamboo as an important pulp and paper raw material. So this table shows the tissue paper production from bamboo in China. And the top line here is the annual output of tissue paper from 2013 to 2016. As you can see, it increases quite significantly. The second line here is the tissue paper production from bamboo pulp. As you can see, it increases even more dramatically. And the third line here is the portion of bamboo pulp in tissue paper. It increases steadily. In particular, the unbleached bamboo tissue paper enjoys its commercial success. In fact, it has a market premium. So it has really a niche market. So this table compares the key chemical compositions between non-wood, in particular bamboo and straw, versus wood materials. As we can see here, in terms of silica content, yes, they are higher than those in wood species, softwood and hardwood, but they are substantially lower compared to those in straws. So for non-wood pulping, in terms of challenges, yes, it contains high amount of silica that is relative to the wood species. Also, it has a high amount of fines and non-fiber cells. Also, in terms of bulk density, it's lower than the traditional woody material, which brings a high cost for harvesting and transportation to the mill sites. This slide shows some morphological features of non-wood. These are the SEM from the cross-sectional area, compound, and wheat straw. And these are the light microscope from compound, wheat straw, and rice straw. As we could see here, in addition to the usual fiber cells, there are many non-fiber cells like the vessel elements. Certainly, they do have a significant impact on the pulping and particularly the paper making processes. For non-wood pulping, the advantages including usually they have lower lignin content. And for that reason, usually it needs lower pulping chemical requirements and less intensive pulping conditions, such as lower temperature and short pulping times. Because of this, for many non-wood materials, in addition to the conventional pulping, alternative chemical pulping processes are applicable. So for the alternative chemical pulping processes, they may include organic acid processes, organic solvent pulping processes, and alternative alkaline pulping that is mainly potassium hydroxide as alkaline source instead of sodium hydroxide. Ammonium sulfide pulping, in these two processes, usually the spent liquor would be utilized as a fertilizer for local fields for agriculture purpose. An alkaline sulfide anthraquinone methanol process, which is also applicable, in this case, it is a modification of the standard alkaline sulfide pulping process. And also the impregnation, delignification, and extraction pulping process, the so-called IDE concept, can be applicable. And last not the least, inorganic acid pulping, such as nitric acid. Due to the limited amount of time, I'm not going to cover all of them. But as I said, the entire review paper has been just published in Biofuels, Bioproducts, and Biorefinery Journal. So for organic acid process, the advantages include, yes, the process offers higher pulp yield. The pulp produced has usually lower copper number, and the chemical process is usually done by distillation and therefore the capital cost will be much less compared to the conventional alkaline spent liquor recovery process. The drawback is that due to the acid nature, it has higher demand on the digester construction materials. Usually has to be anti-corrosive. So this shows the flow sheet of organic acid pulping of non-wood. As you can see, the process produces bleached pulp and lignin from the spent liquor, and together with ethanol through fermentation of the dissolved sugars from the spent liquor. The formic acid is reused or recovered through distillation, and also the process in terms of bleach plant operation is totally chlorine-free. So for the alternative alkali pulping, as I mentioned, mainly it is focused on potassium hydroxide instead of the conventional sodium hydroxide as alkaline source. So the process itself is environmentally friendly. The spent liquor is used as fertilizer for the local fields. Also, the pulp produced has a comparable bleachability to the conventional pulping process from non-wood, and also has similar paper-making properties. So this is the flow diagram of potassium hydroxide pulping of rice straw following biorefining concept. Of course, this is only the idea, right? It's not materialized. So in this case, bleached pulp is produced, and from the spent liquor, you produce or you extract silica, lignin as a product, and then ethanol would be produced through fermentation from the dissolved sugars, and the remaining potassium-rich spent liquor can be used in the field as a fertilizer. For organic solvent pulping, of course, we do understand that it does offer some advantages. First, it is sulfur-free process. Usually, it offers higher pulp yield compared to the conventional pulping process. Also, the chemical recovery process is much simpler because it's based on distillation. And also, from the process, your lignin and hemis are produced as co-products. The drawbacks is that because of the presence of solvent, which has higher volatility, and therefore the digester needs to operate at high pressure. For the alkaline sulfite anthraquinone methanol process, the pros is that the process is applicable to broad spectrum of non-wood species. Also, the process offers high pulp yield and more delignification. The cons is that, again, due to the presence of methanol, the digester needs to be operated at high pressure. For the inorganic acid pulping, yes, again, the spent liquor is used as a fertilizer, and the process operates at a lower temperature compared to the conventional process. The pulp produced has a good pulp quality. And again, due to the acid nature, it needs acid-proof material for constructing the digester. For the future perspective, and certainly, the local supply of raw material needs to be operated in a sustainable manner, and the farmers need to be involved in the value chain optimization, and it follows so-called cooperative society concept, which was proposed. Okay, for this cooperative society biorefinery, so in this case, various agricultural wastes, including wheat, straw, rice straw, etc., essentially are collected through the farmers and then supplied to a small pulp mills, which are kind of operated in satellite pulp mills. And then this pulp is produced, can be transported to a paper mill, which of course in larger scale, from where paper products are being produced. And then of course, from the pulp mill, from satellite pulp mill, in addition to the pulp, you have lignin and hemis are produced as co-products. So this table essentially compares the pulp quality or the pulp characteristics from the alternative chemical pulping process of non-wood in reference to the conventional pulping process of non-wood. As we can see, the pulp yield are usually comparable or slightly higher compared to those in the conventional pulping process of non-wood, while the kappa number are similar or slightly lower compared to the conventional pulping process of non-wood. And here there are other processes of alternative chemical pulping. Again, in terms of the pulp characteristics, for pulp yield is similar or slightly higher compared to those of conventional chemical pulping of non-wood, while the kappa number are similar or slightly lower compared to the conventional pulping process of non-wood. So to conclude, we say that agricultural residues, of course, certainly have lower bulk density and spread over a long distance. And therefore, a small mill operation, kind of satellite pulp mills, are practical. And those pulps then are produced, transported to a big paper mill operation from where paper products are produced. So the high silica content in wood certainly restricts its use in the conventional pulping process, which also opens at the same time the door for alternative chemical pulping. Organic solvent process, of course, are advantageous. In this case, the solvents are recovered through distillation and reused. Potassium hydroxide and ammonium sulfide process are alternative for non-wood pulping. In particular, in this case, the spent liquors are utilized as a fertilizer and no chemical recovery would be practiced. So these alternative processes can follow the biorefinery concept. The lignin dissolved certainly be used as a product. And I understand my friend, Professor Fatahe, is going to give a great talk in about an hour or so in a session 3/2, I think in about an hour or so. So that will be interesting one. And dissolved hemicellulose can be used for biofuel or biochemicals, certainly. And these alternative processes are well adaptable for small-scale biorefinery concept. That ends my presentation. And thank you very much for your attention. And certainly if you would have questions, I'll try to help or answer. Thank you again. Professor Nakagawa, it's yours.
Thank you. Thank you for your presentation, so Professor Nils. So we'll start discussion part. So if you have questions, please write chat or raise your hand using how do you say in Zoom icons. So do you have any questions, audience?
Yes, Mr. Rising.
Yes, thank you very much.
Augusta-san,
Thank you very much, Professor Ni, for the nice talk and review. I'm interested about the inorganic acid pulping. Inorganic acid pulping, I have one question. In today, you said that inorganic acid pulping have advantage in low temperature and good pulp quality. So I want to ask, how about the direct comparison for non-wood between inorganic acid pulping and conventional alkaline pulping? Thank you very much.
Thank you, sir. Good question. Well, in that review paper, which I can send you the link, we compared mainly nitric acid in this case with some conventional chemical pulping of course, the same non-wood species. And usually, indeed, the operation conditions and particular temperature is lower. And pulp quality, I think, is comparable based on these from the literature. But again, I can send you the full paper, which you can survey the results and see the highlights. So.
Thank you.
I hope I addressed your question, Augusta.
Yes, I got the point. Thank you very much.
Yeah, I will send you the link which contains that paper.
Yeah, thank you very much.
Thank you.
Thank you, Augusta-san. So, do you have any questions for audience? So, when chat, from the audience, so when you use KOH for non-wood cooking, it would be expensive without chemical recovery paint. Even so, fertilizer. Sorry.
Yes, we can ask Iwasaki-san. Can you ask?
Well, in this case, Professor Nakagawa, of course, potassium we know is a kind of fertilizer too. So I know at least 1 million in China, and now I'm not so sure whether it's still in operation. They of course sell this what they call organic fertilizer to the field, so you will get some money. I think similar to the potassium-rich fertilizer, Professor Nakagawa.
Okay, so I have one question.
Yes.
So, if you have any idea, utilization of silica, so of course non-wood fiber, so rich silica.
Yeah, well, for the silica extraction and its potential product characterization and applications, Dr. Zhang Han and his colleagues have done, I guess, at least one studies. It's kind of interesting, and they're testing, of course, applications, but I believe that the applications should be expanded, or more studies should be done really to see if the silica coming from this type of material is unique in some properties and particularly suited for some niche or unique applications.
Thank you. So time is enough. So thank you very much, Professor Nis. So,
Thank you, Professor Nakagawa. Everybody enjoy the conference. Thank you again.
Thank you again. Hey. Okay, so next topics we start 9:25 in Japan time. So next speaker is Professor Yokoyama.
I should share now?
Yes.
Okay. Oh. Oh.
いや。
あれ共有しても画面っていうのがねえです。
Yes, I can see your presentation. はい。大丈夫です。Could you turn on your camera? How do you say?
Sorry.
So actually, we can show your slides. It's enough かな。スライドは見えるんですけど、横山先生の顔が見えません。あれ
ビデオオンにしたつもりなんですけど。
あ、見えました、見えました。
見えてます。
見えてます。 まあ、じゃあ、いいかな、その24分。25分。Okay. So, let me move to the next topic. Improvement of delignification selectivity in probably leveraging this process by application of manganese dioxide. Sorry. So, speaker is Professor Tomoya Yokoma Tokoya. ちょっと待って。I'm sorry. So, next speaker is Tomoya Yokoyama. Please start your presentation. Okay.
Thank you, Dr. Nakagawa, for your kind introduction. And ladies and gentlemen, and thank you for organizers to give me this opportunity to make presentation. Okay. My presentation title is Improvement of Delignification Selectivity in Pre-Bleaching Process by Application of Manganese Dioxide. So actually, this is done by this Mr. Shiron Sun. He is a PhD candidate in our laboratory, and he will get his PhD degree probably next March. So first, I would like to introduce this research. As you know, the severe degradation of carbohydrates has still been a serious drawback in oxygen delignification, although the chemistry of oxygen delignification has extensively been studied to suppress it. And the ground state of molecular oxygen, triplet oxygen, which is a reagent of the delignification in this method, attacks only phenolic aromatic moieties in lignin. This is important. And this attack is accompanied by the formation of peroxides, which decompose to generate active oxygen species. These active oxygen species are most responsible for the degradation of carbohydrates in oxygen delignification. This slide shows the schematic reaction during oxygen bleaching and oxygen delignification. Molecular oxygen react only with phenolic moiety in lignin, mostly. Molecular oxygen does not react directly to carbohydrates, And the superoxide anion radical and the phenoxyl radicals are produced. And these combines to lignin peroxide. And there is a discussion whether or not this phenoxyl radical reacts with molecular oxygen to be peroxyl radical. If this is produced, this also degrades carbohydrates. And when this reacts with molecular oxygen, superoxide anion radical can be free and to be disproportionation to be hydrogen peroxide. And this organic peroxide, lignin peroxide and hydrogen peroxide is catalyzed by metal ions to decompose to produce oxyl anion radical at high pH. This is the conjugate base of hydroxyl radical. pK value of hydroxyl radical is 11.9. And these species attack carbohydrates as well as others. This is schematic description in oxygen delignification. It is widely known that manganese dioxide catalyzes the bimolecular self-decomposition of hydrogen peroxide to molecular oxygen and water without formation of any radicals. Following this equation, as you know, this is a topic of junior high school, actually. If manganese dioxide similarly catalyzes bimolecular decomposition of organic peroxides to alcohols and molecular oxygen without formation of any radicals, following the equation, this one, addition of manganese dioxide to oxygen delignification must suppress the degradation of carbohydrates. However, actually, it is commonly known that manganese is not so good for oxygen-related bleachings, right? But anyway, if this is correct, addition of manganese dioxide should suppress the degradation of carbohydrates. Objective of this study is that to examine whether or not addition of manganese dioxide is actually effective to suppress the degradation of carbohydrates in oxygen delignification. And after that, because manganese dioxide is an oxidant under acidic conditions and certainly oxidize lignin model compounds, manganese dioxide can be a delignifying agent. So second objective is to examine whether or not introduction of manganese dioxide oxidation into pre-bleaching enhances delignification, resulting in improvement of selectivity between delignification and carbohydrate degradation. So I would like to shift to result on discussion. First one is addition of manganese dioxide to oxygen delignification. First one is reaction model compound. This is the model compound of carbohydrate methyl beta glucopyranoside, MGP. This is a phenolic lignin model compound, vanilla alcohol. These are together reacted under these conditions, 0.5 mole per liter NaOH, temperature 95 degrees C, oxygen pressure 1.1 megapascal. Manganese dioxide is added at 0.36 millimole per liter. Of course, this is solid, not dissolved, but amount is this one. Molecular oxygen does not directly react with MGP, but with vanilla alcohol to generate active oxygen species, which degrade MGP. The degree of the MGP degradation was examined in the presence or absence of manganese dioxide. So this is the result. This slide shows the result. This is the degradation of MGP, and this shows vanilla alcohol degradation in the presence of manganese dioxide. As you can see here, almost no degradation occurred in the presence of manganese dioxide. This point shows the degradation of MGP without manganese dioxide. So the degradation was suppressed by the addition of manganese dioxide, this level. This level is the degradation of MGP when iron is added together. Very degraded. So at least in model experiments, the addition of manganese dioxide is very effective to suppress degradation of carbohydrate model compound, MGP. Okay, the addition of manganese dioxide clearly suppressed the degradation of MGP. The addition of manganese dioxide was thus expected to protect carbohydrates in actual oxygen delignification process. Thus, hardwood unbleached pulp was oxygen delignified with the addition of manganese dioxide to examine whether or not the addition actually suppresses the degradation of carbohydrates. This is conditions: hardwood unbleached pulp, kappa number 14.2, viscosity 21.5, initial pH 12.5 or 11.5, pulp consistency 4.0%, manganese dioxide addition 0 or 2.5%, auto pressure 0.6 megapascal, temperature 95 degrees C, reaction period Z. Each treatment was duplicated at any data point. And two types of manganese dioxide were used. First one is commercial MnO2, and second one is synthetic MnO2. Synthetic manganese dioxide was synthesized from manganese 2+ by O2 oxidation at the alkaline pH. Manganese 2+ means a solution of manganese sulfate. The oxidation powers of 1 and 2 are 90.2% and 84.9% respectively, based on the theoretical value. But the degradation of lignin model compound by these two, when compared these two, the oxidation rate by using synthetic one. Sorry, what happened? Synthetic one was faster, even though oxidation power is lower. So this is because probably physical property like crystallinity or crystal form, something like that. Okay, this slide shows the result of the oxygen delignification, and this This slide shows what x-axis is kappa number and y-axis is viscosity. And pulping starts around here, and this is 40 minutes result. This is 80 minutes result, 120 minutes result, 24-hour result, 6-hour result. So the lignification proceeds, point becomes right, and the viscosity drop is low. So I call this one reaction selectivity between delignification and carbohydrate degradation. If you can see data point around this area, that is very high selectivity. If you can see the point around here, this is low selectivity, not good for bleaching. This area is good for bleaching, okay? And this is the result of reference pulp without addition of MnO2. This is the addition of commercial MnO2. Actually, the result is not so different. This is 40 minutes, 80 minutes, 2 hour, 4 hour, 6 hour. And this is the result of using synthetic MnO2. Actually, not so different reaction selectivity, 40, 80, 2 hour, 4 hour, 6 hour. So actually, the result showed that the addition was not so effective or no effect, actually, not so bad or not so good. At initial pH 12.5, that one was initial pH 12.5. In the reference oxygen delignification for 6 hours, the prepared pulp had a kappa number of 7.2 and viscosity 12.2. In the commercial, not so different. Not only commercial, but synthetic, the result was not so different. Thus, the addition of either MnO2 was rather inert, actually. Initial pH 11.5, we also did this one, but the result is also not so different, actually. Because kappa number decreased from the original 14.2 only to 10.8 or 10.7, and further delignification could not progress at an initial pH of 11.5. 12.5 seems to be better in this study. So no clear difference was observed in the selectivities between the reference and MnO2 added oxygen delignifications. So we attributed this result to a presumption that solid MnO2 existed outside pulp fibers and hence could not affect chemical reactions occurring inside them. We tried an oxygen delignification in the presence of MnO2, which was generated inside in pulp fibers. So MnSO4 was added to a suspension of the hardwood unbleached pulp at a pH of 2, and this MnSO4 is soluble in pH 2. MnSO4 dissolved at this pH and free Mn2 plus penetrated into pulp fibers. After that, the suspension was alkalified to be a pH of 12. Then manganese 2 plus and manganese 2 plus related species in pulp fibers were oxidized by O2 bubbling. After the oxidation, probably MnO2 was produced in pulp fibers, and the delignification was conducted under the same conditions. But probably all the Mn-related species may not necessarily have existed as MnO2. This is the reference data I already shown, the same one. And this is MnO2 added in pulp fibers. Actually, the results are very bad when compared with reference. So it means the degradation of carbohydrate was enhanced by the addition of MnO2 in pulp fibers. So the selectivity in the presence of MnO2 generated inside in pulp fibers was clearly worse than that of the reference. This result must originate from the fact that the oxidation of Mn2 plus to MnO2 in the fibers was not complete. This incomplete oxidation must have left Mn3 plus related species, as well as others, which promoted the formation of active oxygen species quite differently from MnO2 in the fibers. Actually, Mn3 plus related species is active to catalyze the decomposition of peroxides to form active oxygen species. So if these species present, the activity is very different from MnO2. So we think that this is the reason, probably, Finally, any addition of MnO2 were not able to finally attain a high selectivity against the result of the model compound experiment and our expectation. So instead, we tried substitution of Mn2 oxidation stage for the latter half of oxygen delignification. Because MnO2 is an oxidant under acidic conditions and certainly oxidizes non-phenolic lignin model compound, MnO2 is a possible bleaching agent. We examined the effect of substituting MnO2 oxidation stage for the latter half of oxygen delignification. Because MnO2 is re-prepared from Mn2+, which is a waste matter of MnO2 in its oxidation stage, by auto-oxidation and alkaline conditions, recycle of manganese dioxide can be expected as another advantage. This is conditions. First, common oxygen delignification was conducted for 2 hours. After that, manganese dioxide oxidation stage was conducted. Conditions are these here, shown here. This is reference data, oxygen delignification. At this point, oxygen delignification was stopped for MnO2 oxidation stage. This is the result. Oxidation, MnO2 oxidation at pH of 2.0 is this one, and 1.0 is this one. So if pH was 2.0, reaction selectivity becomes higher than just only oxygen delignification. But when we use sulfuric acid for pH 2.0, the amount of acid is small. And at this point, final pH was 3.7. Already MnO2 cannot work as oxidant. So after that, we use sulfate buffer at a pH of 2. And we can extend delignification with good reaction selectivity when compared with reference oxygen delignification as like this. So the selectivity was improved by substituting the MnO2 oxidation stage at the pH of 2 using sulfuric acid for the latter half of reference oxygen delignification. And instead of sulfuric acid, when we use sulfate buffer, the result was better, can extend the delignification. And finally, kappa number was 5.3 and viscosity was 12.0. The degradation of carbohydrates was severe when the manganese dioxide oxidation stage was conducted at a pH of 1.0. The manganese dioxide oxidation using sulfate buffer at a pH of 2 could not largely delignify when it directly applied to the unbleached pulp without common oxygen delignification in the former half. So that's conclusion. The addition of manganese dioxide suppressed well the degradation of methyl beta-D glucopyranoxide, a carbohydrate model compound in the treatment, simulating an oxygen delignification process. However, the addition of either commercial or synthetic MnO2 was rather inert in the oxygen delignification of hardwood and bleached pulp, which must have been attributed to the presence of the manganese dioxide outside pulp fibers. The addition of manganese dioxide generated in situ in pulp fibers unfortunately resulted in the enhanced degradation of carbohydrate in the oxygen delignification of hardwood and bleached pulp, which must have been attributed to the incomplete degeneration of manganese dioxide in the pulp fibers. Selectivity of the whole pre-bleaching stage was improved well by the substitution of the MnO2 oxidation at the pH of 2 for the latter half of common oxygen delignification. This is sulfate buffer. Thank you for listening. That's it. Can you listen? Dr. Nakagawa?
Excuse me. So, excuse me, sorry. So we'll start discussion part. So do you have any questions, audience? So Professor Nis, so please ask to Professor Ni.
Okay. Thank you very much, Professor Yokoyama. Very nice work and very clear, I guess, in terms of logics and the experiment design. So at the end, you and your student found that, well, one magnesium oxide in this case was used in the second half of oxygen delignification. This is done on acidic conditions, so in this case, magnesium dioxide is functioning as oxidant. So then, is there any function as a radical scavenger per se under this condition, or it is mainly as oxidant now?
Yeah, probably this is just oxidant, I think. This is just at pH 2.0 using at 70 degrees C. Of course, some radicals are produced probably, but I cannot say about radical reactions at this condition actually, but
so it's mainly as oxidant.
Probably,
right?
Probably, I believe.
So it's a bit deviated from the original idea of try to destroy the radicals present in oxygen delignification, therefore improving the selectivity, I guess.
After half, actually in this MnO2 oxidation stage, oxygen pressure is not supplied, just atmospheric pressure. Anyway.
Okay.
Yes. So I believe not so radical species are working. Yeah, of course, some radicals are produced probably.
Yeah, thank you. Okay, I stop it over here, Professor Nakayawa.
Okay. So audience have questions in chat. So audience have questions of filtrate in so oxygen breathing in MnO with MnO2.
I'm sorry.
I read so.
Well, if so quiet, may I have a second question, Professor Nakayawa?
Yeah. So audience have questions of filtrate so oxygen breathing. So すいません。
I should see by myself, actually. Oh. How can I see?
So I read
yes, please. Sorry.
So how about the filtrate of this oxygen breaching MnO2? Is it still possible for chemical recovery? Or it will need treatment before sent to the recovery plant?
Yes. After okay, when MnO2 oxidizes lignin, it becomes the Mn2 plus. It dissolves in acidic solution. So if MnO2 amount is just a good amount means equivalent amount to lignin, residual lignin, most of MnO2 is converted to Mn2 plus, and most Mn2 plus dissolve in liquid. So if you filtrate it, Mn is moved to filtrate, not on pulp fibers. And after that, if you oxygen oxidize this filtrate, under alkaline condition, you can get again MnO2. So probably the cycle is okay.
Thank you very much. So time is enough. So we close second for presentation. Thank you very much, Yokoyama. So I apologize for my organization.
Thank you for everybody for listening.
Okay. Please close your presentation. Okay, so next speaker, so Dr. Takahashi, please share your presentation. Okay. Okay, I can see your presentations. So I introduce so next topic, so preparation of softwood soda lignin based water reducer for concrete. So Dr. Takahashi, please start your presentation.
Thank you, Dr. Nakagawa, for your kind introduction. Today, I'd like to talk about preparation of softwood soda lignin-based water reducer for concrete. So first of all, let me introduce what is water reducer for concrete. Water reducer is a widely used concrete chemical mixture. It can increase the fluidity of fresh concrete and reduce water content in fresh concrete. So the workability of fresh concrete and the concrete strength can be increased. The performance of water reducer can be evaluated by mortar flow or a concrete slump flow test like this picture. Mortar is a mixture of water, cement, and sand, and concrete is a mixture of all these materials. A flow value means the diameter of mortar or concrete, and it's an indicator for cement dispersibility. Higher flow value means better performance. Polycarboxylate, naphthalene sulfonate, and lignosulfonate are typical commercial water reducers. Polycarboxylate and naphthalene sulfonate type are fossil resource-based synthetic anionic surfactants. These two types show higher cement dispersion and water reduction than lignosulfonate. So generally, the order of their performance is like this. As you know, since we have abundant resources of Japanese cedar in Japan, we have been developing lignin-based water reducer from Japanese cedar as highly value-added functional materials. In the previous study, we have investigated the potential of Japanese cedar soda lignin as water reducer. We prepared soda lignin from black liquor, and we evaluated the performance of soda lignin with mortar flow test. This is the mortar flow value of commercial lignosulfonate. Our soda lignin had more mortar flowability and showed better performance than lignosulfonate. So in this study, we will focus on the improvement of the performance of soda lignin by chemical modifications. Next, let's see the mechanism of dispersion of cement by commercial water reducer on next slide. If we don't add any water reducer in cement, cement particles are aggregated in water and mortar flow value is low. If we add water reducer, the molecule of water reducer can be absorbed on the surface of the cement particle through their anionic groups. And then cement particle can be dispersed via two forces. In the case of naphthalene sulfonate and lignosulfonate, they give the cement a slight negative charge. This negative charge creates electrostatic repulsion force among cement particles. In the case of polycarboxylate, side chain polyethylene glycol PEG chain physically helps cement particles disperse via steric repulsion force. Generally, steric repulsion introduces larger dispersion force. So, anionic groups and side chain molecules are important to design the high-performance water reducer. So, based on this mechanism, to improve the performance of soda lignin as water reducer, PEG chain function as steric repulsion force and or carboxyl group function as absorption site on cement were introduced to soda lignin. To introduce PEG chain and control the chemical composition of lignin PEG derivatives, we used PEG monoepoxide. And to introduce carboxyl group, we will apply ozone treatment to modification. So objective of this study are as follows. First, the softwood soda lignin was modified with PEG with various chain lengths to investigate the effect of PEG chain lengths on the performance as water reducer. And the softwood soda lignin and lignin PEG derivatives were treated with ozone. So first, I'd like to talk about modification of softwood soda lignin with PEG. We prepared lignin PEG derivatives as follows. The epoxide group can be reacted with phenolic hydroxyl group in lignin under this condition. First, soda lignin sodium hydroxide aqueous solution was prepared, and PEG monoepoxide was added to the lignin solution. 3 different PEG chain lengths were used in this study. The number of ethylene oxide repeating unit of 10, 15, and 25 moles. Then the mixture was heated to prepare lignin PEG derivatives. Finally, we conducted the determination of the introduced PEG content by measuring residual phenolic hydroxyl group content in lignin. And we also evaluated performance as water reducer by concrete slump flow test. This table shows modification conditions and introduced PEG content in derivatives. We prepared derivatives having various introduced PEG content in each PEG chain length series. This slide shows the result of concrete slump flow test. The concrete slump flow value is plotted as a function of additive amount of lignin PEG derivative on cement. The value in parentheses is the introduced PEG content in derivative. For comparison, commercial water reducers lignosulfonate LS and naphthalene sulfonate NS were also tested. As you can see, increasing the introduced PEG content, their performance was increased in all PEG chain length series. And lignin PEG derivatives show better performance than not only LS but also NS. And as compared with the best performance in each PEG chain length series, 15 mole derivative tended to show better dispersibility than other shorter one. The longer PEG chain length was suitable for developing higher performance of water reducer. This is because the longer PEG chain can bring more steric repulsion force between cement particles. Next, let's move on to ozone treatment of soda lignin and lignin PEG derivatives. First, we conducted ozone treatment of soda lignin. Soda lignin solution was prepared and the pH of solution was adjusted 4 to 5. Then ozone was added into the lignin sample solution at room temperature. The ozone charge was 0.4 or 0.8 mole per 1 unit of aromatic ring of lignin. The ozone-treated soda lignin were applied to motor flow test to evaluate the performance, and the carboxyl group content of sample was determined, and the detailed potential analysis was also conducted. The detail of this we'll talk later. And lignin PEG derivative with 50 mole of PEG chain were applied to ozone treatment. We used the derivative having 4 different introduced PEG content. The pH of the derivative solution was adjusted 4 to 5. The ozone charge was 0.8 mole. The ozone-treated lignin pH derivative were applied to motor flow test. This table lists the carboxyl group content. As you can see, ozone treatment increased carboxyl group content in soda lignin. When 0.8 mole of ozone was charged, the carboxyl group content about 2 times higher than soda lignin. And this figure shows the result of motor flow test of soda lignin. The motor flow value is plotted as a function of additive amount of cement. The motor flow value of ozone-treated soda lignin were higher than soda lignin and lignosulfonate. The ozone treatment improves the performance of soda lignin as water reducer. The soda lignin was treated with 0.8 mole of ozone, which had higher amount of carboxyl group, showed better performance than that with 0.4 moles. As I mentioned before, an ionic group of water reducer helped to adsorb the water reducer molecule on the surface of cement particle and gives some electrostatic repulsion force to disperse the cement particles. The zeta potential is the electric potential, and the magnitude of zeta potential indicates the degree of electrostatic repulsion between charged particles in a dispersion. So, to confirm this, the zeta potential of cement suspension containing lignin sample was determined. We prepared cement suspension with additives as follows, and the results are shown in this figure. When soda lignin and ozone-treated soda lignin was added into the cement suspension, the zeta potential was increased. The ozone-treated soda lignin show more larger zeta potential than soda lignin. With increase of the carboxyl group content in soda lignin, the zeta potential of cement suspension was increased. So these results suggested that the electrorepulsion force among cement particles with ozone-treated lignin was larger than that with untreated lignin. Next, this slide shows the result of motor flow test of lignin pH derivatives. We evaluated the performance of derivatives which have various pH contents. The value in parentheses is the introduced pH content in untreated lignin pH derivative. The untreated sample is yellow, ozone-treated sample is blue. As you can see, the ozone treatment was effective to improve the performance of these samples. C4 has relatively smaller pH content, and these two samples has higher pH content, more than 60%. But the performance of the ozone-treated derivative of this sample stayed at the similar level. Since the performance of this sample of untreated derivative already being the highest, the ozone treatment could not show apparent improvement on the motor flow test. So this suggests the degree of performance improvement by ozone treatment depends on the pH content of derivative. So we would like to summarize our presentation. To improve the performance of soda lignin-based water reducer, we modified soda lignin with PEG. The lignin PEG derivative performed better than commercial naphthalene sulfonate-based water reducer. The longer PEG chain length was suitable for developing higher performance water reducer. And we also applied ozone treatment. The ozone treatment was effective to improve the performance of soda lignin and lignin pH derivatives as water reducer. And the electrorepulsion force among cement particles with the ozone-treated soda lignin was larger than that with untreated lignin. So this work was supported by the following project. We thank Dr. Hosoya for his assistance and advice in ozone treatment experiment. We also thanks to Mr. Morimoto, Nippon Shokubai, for conducted concrete slump and motor flow test. So thank you for your attention.
Okay, thank you for your presentation, Dr. Takahashi. So we'll open to discussions. So do you have any questions, audience?
Hi, Dr. Nakagoya. I have, this is Pedro Fati from Lakehead University, Canada. I have a couple of questions, if you don't mind.
Please.
Hi, Dr. Takahashi. Thank you very much for your nice presentation. Very interesting. I have questions regarding your modifications.
Yes.
So for PEG, modification of your lignin,
Yes.
have you calculated the degree of substitution, or basically the proportion of your PEG versus the rest of lignin in your product, or basically a molecular weight change after the modification?
Okay, so actually we didn't measure the molecular weight, but we determined the introduced PEG content by measuring residual phenolic hydroxyl group in the derivatives, because we used monoepoxide PEG to modification with soda lignin. So mainly phenolic hydroxyl group can be reacted with epoxide group. So we determine the residual content of phenolic hydroxy group to determine the introduced PEG content. And this is the result of introduced PEG content. So we increased using the amount of PEG monoepoxide. Introduced PEG content also increased. So we haven't determined the molecular weight of lignin derivative, but I think molecular weight should increase by this modification.
Yeah, so that's interesting. So the continued question I have is, if you have seen, let's say at higher dosage of your lignin, if you have seen reversed impact, let's say if you apply more dosage, then you see coagulation and you see reverse impact. Have you seen this?
Actually, we check about additive amount on cement. We didn't see any coagulation. Just let's see if we increase the addition of amount of lignin derivatives, concrete slump flow value is increased.
Okay, so that's interesting. So very short question. You mentioned ozone oxidation, but as you know, when you apply ozone, the yield of your product may drop, basically because you oxidize lignin. Some of them may degrade. So my question to you is, if you considered other ways of introducing carboxylic group, let's say carboxymethylation, carboxypropylation, other carboxy alkylation, because these grafting reactions can also be done in alkaline conditions. So you could have mixed your carboxymethylation with PEG reaction, because in PEG you also had grafting. So both of them are under alkaline condition. You have combined them in one pot and you could have done that. Have you considered this?
Oh, I didn't check your suggestion. Yes, yes. Actually, this idea is very good. But we just check the first pejoration and after ozonation. Thank you for your comment.
Okay, that's really great. The last question, very quick. Have you purified your product after this reaction before adding to cement? Thank you very much.
So we didn't purify the product because if we synthesize lignin PEG derivatives, it also contains untreated PEG, but untreated PEG doesn't affect the concrete flowability. So that's why we didn't purify the sample. We applied that directly.
Thank you.
Thank you.
Okay, thank you very much. So time is now. So I will close this session. Thank you very much, Dr. Takahashi.
Thank you very much.
So next session starts so in Japan time, so 22:15 かな? So next chairperson is Professor Yokoyama. Okay. Thank you very much. So I'll close session 3-1.
So, good evening, everybody. I am Tomoya Yokoyama, the chairperson of next session. Session number is 332. The content is lignin. So next speaker is Dr. Fateh. Am I correct? Sorry. Please prepare your presentation. Dr. Fateh. I'm sorry. My pronunciation correct?大井先生、おられますか、その方。
Just before he asked a question to Shinko Takahashi, Professor Fateh. Yeah. He is now preparing. Professor Fateh, can you share your PowerPoint presentation with us? Okay. Dr. Ayub, how are you? You are next to Fateh's room? No? Student room? Okay, thank you. Yes. Pedram, it's your presentation.
Hi, yes.
Yes, can you share?
Sure.
You have 50 seconds. Okay.
Can you see this?
Yes, thank you.
Yes.
So your chairperson, Yokoyama-san, please.
Yes, but still 14. Is it okay?
So let me know when I can start.
Wait a moment, please. Okay, my name is Tomoya Yokoyama, session chairperson of this number 32. The first presentation in this session is from Dr. Fateh. I'm sorry, am I correct? Dr. Fateh. The title is current. Sorry, title is current status of lignin-based dispersant and flocculant productions. Okay, so please, Fateh. Dr. Fatih, please.
Good morning and good evening to all of you. I hope you are enjoying your time, and thank you very much. I would like to thank you very much, the organizer, for this conference. It's really great. I have learned a lot. So the topic of my presentation is basically the current status of lignin-based flocculant and dispersant production. So basically, I want to focus on what we have done in the past few years, what we have made, and what's the current status of this this material. So so this is the abstract of the work of I think 20 graduate students, but for this presentation, I've had help from my postdoctorate fellow, Dr. Ayub, and Jonathan, who is my PhD student. So flocculant application. So as you know, in municipal and industrial wastewater and water purification processes, lots of flocculants are used. So they used to for cleaning the water, cleaning wastewater before releasing to environment. In tailing waste, in oil production, in oil and sand, in mining, they use a lot of flocculants in their wastewater treatment system. In mining, we have lots of thickeners, we have lots of clarifiers, basically in chemical industry. They use a lot of flocculants to clarify the suspensions they have. However, basically, we have two types of flocculant. One of them is inorganic coagulant like alum, but because they are inefficient, so to get a good flocculation efficiency, they use a high dosage of this alum, which generates a secondary pollution by introducing large volume of sludge. So that's not good. They clean the water, but they produce lots of secondary pollution, which is the basically the sludge production. And this is one big problem of many wastewater treatment systems. Then we have synthetic flocculant, like polyacrylamide. They are expensive, sometimes ineffective, and they're oil-based. So the production of polyacrylamide in 2013 was almost $4 billion. This is the polyacrylamide used only in wastewater treatment, not the whole production or sales. In 2019, it was almost doubled. So we can see that the use of polyacrylamide in a wastewater system is getting higher and higher. If you look at the dispersant, where do we use dispersant? For all paint stains, we use a lot of dispersant. Froth flotation in the mining industry, construction industry, as Dr. Shiho mentioned. So they are used as water reducing agent in textile industry to disperse dyes in suspension, in cold water slurry, which is a new generation of fuel, so to say. We need to use a lot of dispersant. In ceramic industry, in clay suspension, we use a lot of dispersant to make sure that the suspension is homogeneous. So we have a lot of use for dispersant in the chemical industry. However, as Dr. Shiho mentioned, mainly polyacrylic acid, polymetamacrilic acid, and sodium naphthalate. They are expensive and they are oil-based, and sometimes they are ineffective. So we need better flocculant, better dispersant, and we need them to be bio-based. So that's the message we have. But now, if we look at what we have been doing in the past 50 years, basically in industry, you can find information on the starch-based, cellulose-based, cartazan-based, flocculant dispersant. But these materials, we have a lot of other uses for them. Starch we eat, it's our food. Cellulose we use in papers and other products. Chitosan as well. We can use a lot in many fields. But lignin, it's a biomass. It's a part of biomass. It's underutilized. We have only burning this as a commercial, use for that. So we don't have any commercial. Maybe here and there you can find some processes, but when you look at the large volume of use, it's mainly for energy. So if you look at what's going on in the other, apart from energy, the only reports that we have had in the past was the use of lignosulfonate. So lignosulfonate have been used for other purposes, as Dr. Shiho mentioned, for example, in concrete. But as we know, its production is limited because that depends on the number of sulfide pulping processes we have. And we don't have too many these days. We have mainly craft, and they are converting or they are shutting down. So the lignosulfone production is getting more and more limited. And if you look at the chemistry, we have only one sulfonate group per unit of lignin. That means that the functionality of this lignosulfonate is also limited. And of course, it has some sugars as impurity, that's also affecting the product quality. So we reviewed this in our review paper. If you're interested, you can look at that. Apart from that, if you look at the patents, there are patents available for lignin polymerization, for lignin reaction in this area, but they are mostly solvent-based or alkali-based reaction. So solvent is good, you can produce whatever you want, but it's not that interesting for pulping industry. So basically you can't adopt solvent-based process to craft process or to sulfide process easily because of the difficulty we have with solvent. And under alkaline condition, the reactivity, the reaction as we have investigated is not that great. Opportunities. Well, we have a lot of lignin. Wherever we have wood or non-wood, we are talking about 20% to 40% of the material being lignin. So it's widely available everywhere. And also, this is very important fact. If we want to have any biorefining process to utilize biomass, whether it's agro or wood, doesn't matter. We cannot just talk about carbohydrate. We cannot just utilize carbohydrate and leave wood, or leave lignin unreacted or underutilized. So basically, we cannot just ignore 30%, 40% of the biomass. We have to utilize all of them. And that has been a challenge for many, many biorefining processes introduced in the past 10 years because they didn't have a method or a solution for lignin. So utilization of lignin is critical in many biorefining processes. So this is the opportunity we have for lignin. So I have different sections. We have done many different we have had different approaches in dealing with lignin. I'm going to overview some of them. I'm not going to go to the details because there are a lot, but I'm just going to introduce to you what we have done and what we have achieved. In terms of oxidation, we wrote a review paper published last year. If you're interested in tempo oxidation of lignin, we have reviewed this one in this paper. We discussed if you do this, if you do that, if you do solvent, if you do aqueous, if you do versiver, if you don't do versiver, what's going to happen in lignin based on literature, available literature. In terms of the research we have done, so the first thing we did was basically hydrogen peroxide oxidation of lignin. The results is available in that paper. Basically, we oxidized with hydrogen peroxide, and then we had oxidized lignin with some carboxylic group. We measured the charge of that. And as an indicator of its dispersion, we use that one for dispersing kaolin suspension. As you can see, in the wide spectrum of pH for kaolin suspension we have had, when we add our oxidized craft lignin, the particle size of this clay suspension drops. So that means that we had some dispersion in the system. The other thing was that basically, if we compare lignosulfonate and our oxidized lignin, when we add more dosage, we had better or higher relative turbidity in our sample. So that means that our sample made the kaolin suspension more turbid. That means that we have better suspension in the system. So that's an indicator of better performance of our sample compared to lignosulfonate. By the way, this lignosulfonate is the one we purchased from Sigma, so it's commercially produced. In another research, we wanted to design dispersion. We wanted to generate dispersion again by oxidation. But in this case, we wanted to see how the charge density and molecular weight of, let's say, dispersion would impact the kaolin suspension. So we had two basically categories in this one. We had samples with the same molecular weight of 30,000 gram per mole. Basically, but the charge was different from 0.5 to, I think, 4. The other one, we had the same charge of 3, but the molecular weight varied from 10,000 to 80,000. So these lines, this is the dosage, but each line represents one charge density. And what we have seen is that this one, I don't have the data here, the highest charge, which was around 3.6 to 4, that generated the best dispersant. When we had the molecular weight impact, we have seen that when the molecular weight gets higher than 40,000, if we add too much, then at some point we see some turbidity reduction. That means that we had coagulation, and basically coagulation and or flocculation. So that means that the molecular weight is an important factor. So the higher molecular weight, when we moved from 10,000 to 40,000, which was from the blue to the green one, we had better performance, even at higher dosage. But when we had the higher molecular weight, basically we had to be careful. So again, as Dr. Shiho mentioned, if we add, the molecular weight, the degree of hairing, let's say on particles is important. If we make it too hairy, or if we adsorb material with a long hair, they may help coagulate. They may help flocculate the samples. So the message we had here is that the higher the charge, the better the flocculation, but molecular weight should be taken care of and do not go over 40,000. And we did this research, we did a similar research, but using another suspension, and we had another lignin, and we reached to the same conclusion. So we tried here different lignin. This time was hydrolysis lignin. Hydrolysis lignin, this is the enzymatic, the lignin that was produced by enzymatic fermentation of biomass. So it's very different. It was not Kraft. We oxidized that one with the peroxide, and we use it as a coagulant for aluminum suspension. Alternatively, we have done oxidation of lignin with nitric acid, and we generated some results. And basically, we reported our results in these papers. If you're interested, you can look at them. But pretty much, we report the same performance. If you increase the carboxylic group on lignin, you get better performance. And the maximum carboxylic group content we have had was around 4 millimole per gram. In terms of other grafting, so this is the other approach, not oxidation, we are grafting groups. So we are introducing different groups to lignin. And in this review paper, we discuss what happens if you introduce different groups to lignin. I invite you to read this if you're interested in the grafting reaction of lignin, basically. So basically here, we have had cationic modifications. So we introduced basically this group with cationic, charge density under alkaline condition, and we produce cationic lignin, and we use that one for removing dye. And as we have seen, by increasing the dosage, at some point we get the maximum removal. And when we go over that optimum dosage, we see a charge reversal and dispersion. So this is pretty typical when we use coagulant for dye removal. So the dosage is important. But what we have seen is that the coagulation efficiency basically was good. We have done a similar one for basically we grafted these two tannic acid and Kraft lignin and use it for oil water emulsion. So you can also look at that one. In terms of other other reactions, we have done carboxy alkylation. In this review, in this paper, we introduced carboxy ethylation. We did on lignosulfonate. We have done carboxy propylation, carboxy pentylation. We have done on lignosulfonate. We have done on Kraft lignin. And pretty much what we have seen was that by increasing the chain length of this reagent, we get a better coagulation. So basically, if we have more carbon, we have better efficiency. But this is very different from polymerization. I'll talk about polymerization later on. But so here we have different alternatives. We compared this. LS is lignosulfonate, so you can see that all of our products perform better than the commercial lignosulfonate. So even at same charge density. So I think in this work, we control the charge density to be the same as lignosulfonate, but because we have had different materials, And in this case, we have more carbon chain length, they perform better. So the message here is that the length of the heavy stuff we add to lignin plays very important role in its functionality when we use this one as a coagulant. The other thing is that when you add different reagent, the chemistry could be a little bit different. So again, depending on what chemistry you want to follow, if you want to do under alkaline condition, under neutral condition, under acidic condition, you may choose different reagent to generate lignin or sulfonated lignin with, or carboxymethylated lignin with similar properties. So here, we did sulfamethylation of softwood, and we use this one as a cement dispersant for cement. This one, we did it in 2016, I think. This was published in 2016. So here, basically, we have had oxidation prior to sulfamethylation. So this is only sulfamethylation. This is oxidation prior to sulfamethylation. And this is lignosulfonate obtained from the market. And you can see that the best sample we had, the absorption was better when we had oxidation before sulfamethylation. This is the impact of charge density for the same material. By introducing more charge density or more charges to lignin, we got better results. So the message here is that introduce more charges to lignin, you get better performance. And when we compare the performance of this one with sulfonated lignin, we got the same pattern. The higher the charge, the better the performance. And obviously, we had better performance compared to lignosulfonate. So this is commercial lignosulfonate. This is our sulfamethylated lignin without oxidation. This is with oxidation. And you can see that there's a big gap. Now, sulfalkylation. I talked about carboxyalkylation, now sulfalkylation. Same idea, different chain lengths, but here we have sulfonate group. So basically, if you introduce sulfonate group with different carbon chain length, you get different materials. But the difference of sulfalkylation and carboxyalkylation is that the sulfonate, the pK of sulfonate is around 1 or 0.9. That depends on how the group is. But the pK of carboxyl group, as we know, is around 4.7. So the functionality of this sulfalkylation will be different from carboxyalkylation because it's pH sensitive. So if you reduce the pH, if you have an application for pH 3, I should say that you should go ahead with sulfalkylation rather than carboxyalkylation because carboxyalkylation is inactive at that pH. So, but if you're interested in basically pH sensitive material, carboxyalkylation is a way to go. So the overall outcome we have had is that we have done a lot of grafting under acidic condition, alkaline condition. We have done aqueous and non-aqueous. We may have some chemical industry who are interested in solvent-based processes. We have done oxidation. We are doing more routes. Some of them are suitable for pulping. Some of them are suitable for other chemical, companies. Generally, the molecular weight is not going to exceed 50,000 gram per mole. The charge density cannot go really higher than 4, but this is sufficient for all suspension system we have tested and we have seen in the market. So basically 4 is sufficiently enough to have a good dispersion. But what we have seen is this. This is the structure of lignin we have seen in the, based on reported. You can see that there are some groups here, there are some groups here. Some of them are accessible, because there's no steric hindrance. But when we get here, it's messy. You can't react chemicals with here because of the steric and physical constraint we have. So what we have seen is that if you want to do grafting, it matters if it goes here or it goes here, because here is easy to go, here is not easy to go. That's why when we do reaction on paper, if you have phenolic group of this much or we have aliphatic group of this much, we can easily calculate the theoretical value. But when we do the reaction, because of the physical and chemical constraint, that's not going to happen. So it's difficult to reach to ideal or theoretical value because of the physics of lignin, because of the physical chemical constraint we have. The second one was polymerization. We have done a lot of polymerization to generate anionic lignin, to generate cationic lignin. And this time we wanted to produce high molecular weight because we were interested in producing flocculant. So We have done quite a lot, and we have 2 patents on this one. So basically, here we produced lignin acrylic acid that we compared with homopolymers, or basically polyacrylic acid. They were produced all under the same condition. But what we have seen is that our lignin AA performed much better than PAA when we produce them under the same conditions. And of course, the solubility of lignin is going to improve a lot when we do polymerization. And we have a solubility drop because of the pK of carboxyl group we have on lignin. So we talked about this in this paper. We have done a similar one with the cationic reagent, and this one was our cationic reagent. But this time it's soluble over the all pH range we have studied. Basically, we have used many different cationic monomers, DADMAC, and many. We studied the impact of molecular weight. If we control the molecular weight, what's going to happen? If we control the charge density, what's going to happen? If we, I'm going wrong direction. If we have 2-component system, what's going to happen? If we have 3-component system, what's going to happen? So we have some papers. If you're interested, you can read them, and of course, you can contact me if you have questions. Also, we did some fundamental study to see if we have the same group, but one of them has more methyl group, let's say on the branch, what's going to happen on the flocculation efficiency? For example, here we have 2 the same monomers, but one of them has one extra methyl group. So how this methyl group would impact the reaction, the polymerization, and the product performance, because that's very important. One monomer could be cheaper, the other one would be expensive. If we do reaction under the same condition, do we get the same? And that will be important for commercialization because, the price would change, the efficiency would change. And what we have seen is that no, they are indeed very different. This is the SEM image of the product. You can see that we get a lot larger particle when we use this monomer versus this one compared to our kaolin. And when we did the flocculation, we can see that the flocculation, the length of the particles or the chord length of the particles increased a lot when we use this monomer versus the other one. And also the count of particles. So when the count drops, it means that they flocculated already, they settled already. And of course, when we do the RPM, we see different performance. So the message here is that it does matter what we select what monomer we select for polymerization, even if we control the molecular weight, even if we control the charge density. Then we applied the polymer we had and compared them with commercial ones for a sludge dewatering, for example. Compared to the commercial CPAM, our material, one of our lignin, performed much better in sludge dewatering. When we compared with the commercial or the synthetic one, our product generated much better flocculation because we have better relative turbidity drops. When we use this one in municipal wastewater of our city, again, our lignin polymers drop the flocculation, the turbidity, a lot better than the polydadmac or the one they are using. COD also, another indicator. Our polymer perform much better than what they are currently using. So, again, we discuss more details, synthetic of 2 monomers, 3 monomers, their self-assembly because that impacts their shelf life. If you are interested, you can go to that. But again, we have had some difficulties. And difficulty is that if you want to attach the monomer to lignin, this is what's going to happen. They may attach here, may attach here, may attach here. And if we do the polymerization, that's what we are going to have. We will have 3-dimensional macromolecules with hydrophobic and hydrophilic ends. This 3-dimensional macrostructure affects its performance significantly. So that's why we have much better performance in lignin polymers compared to the other commercial available flocculants. Why? Because there are hydrophilic group. This is the lignin, which is hydrophobic, hydrophilic. Then we have, when we add this to the material, we may have charge neutralization.
Excuse me, Dr. Fatih?
1 more minute.
Okay. Actually, time is coming.
Okay, one more minute, I'm done. Yeah, so this three-dimensional structure will impact as you see, we have blanket effect. So that means that the three-dimensional structure of lignin will push everything down, and that's why we have better performance compared to the linear polyacrylamide or other polymers. Commercialization strategies, we have patents, we are pushing for commercialization. We have tested the impact of different lignin sources, alkali, hydrolysis, softwood, hardwood. We improved the concentration to 50%. We have good results, and we are pushing for commercialization, and we have some strategies, how we can produce anionic lignin, cationic lignin for company A, company B, and so on in the product. So this work was sponsored by many federal agencies, by private companies, as you have seen here. And this is the work of more than 20 graduate students we have had in the past 5 years. Thank you very much, and sorry for this kind of lengthy presentation. Thank you.
Thank you for Dr. Fatih. So actually, time is coming. Is there any? Do you have some question? But a very short one only, if somebody has it. Okay, Dr. Samodra.
Yes, I have a short question. You focus on the production of the flocculant and dispersan, right? But what is your opinion about the blending lignosulfonate material with the commercial polymer, like sulfonated polyethyl ketone for the membrane production? What is your opinion about this one?
For membrane production, what you want to produce is basically insoluble polymers. I did not talk about that in the presentation because the topic was on soluble polymers. Yes, you can. We have produced lignin, meta-acrylic acid, that's water insoluble. We have done lignin styrene. We have done, you can follow similar chemistry. We followed free radical polymerization chemistry. You can follow the same one. You can follow emulsion polymerization. You can follow ATRP. You can produce insoluble lignin. We have produced films. Yes, you can do that. But again, more research is needed in that and to get better results. We are doing this, but we haven't. I didn't present that in here. Thank you.
So thank you, Dr. Fatih. Thank you.
Thank you very much.
Thank you. So, thank you. So next speaker, please prepare next presentation. Who is next presentation? Dr. Xiao Jiang from North Carolina State. Can you share your presentation?
Sure.
Okay, I can see it. Probably everybody can see it now. So please use slideshow. Okay. So next presentation is application of various lignins in phenol formaldehyde adhesives. Presenter is Dr. Xiao Jiang from North Carolina State University. So please, Dr. Jiang.
Thank you, Professor Yokoyama. Good evening and good morning. So I promise this is the last presentation, especially for friends in Japan. After this presentation, you guys can get some rest. So now I would like
to share. Wait a moment, please, Dr. Jin. We can see probably not only current slide but also next one and some others.
Let me see. Let me do that again. Let's see what happens. Weird.
Okay.
I think it's in the wrong window, I guess. How come?
It should be okay, actually.
If you guys don't mind, let me see.
Oh,
Okay, better,
okay.
better.
Yes.
Okay. Sorry about this. I want to share about our research of using lignin in adhesive application, specifically for phenol formaldehyde. So, as you all know, lignin is a natural phenolic polymer, accounts for 20 to 30% of the wood. The technical lignins are mainly isolated from pulping and biorefinery process as a byproduct, and its structure went through different degree of changes, like, for example, degradation or condensation, and also it's the actual structure of your lignins depends on your source, source of biomass, and also the isolation process. And also currently a majority of lignin is burned for energy, but we have some commercial available lignins. For example, like a bio-choice lignin, which is sold by Domtar, and also Indulin AT. It is also a pine craft lignin sold by, before it was Midwest Vaco, right now it's Ingevity. And it give us like a potential. We have this lignin available. We can use it for something. And as for the application of lignin in phenol formaldehyde, actually it's not a novel topic. It has been studied for decades, and right now there's a growing research interest as using lignin as a phenol replacement. And obviously lignin has an advantage of low cost, and compared to phenol, potentially it also can reduce the formaldehyde usage. But lignin is perfect. It has disadvantage as a low reactivity for cross lignin, as you can see from the bottom. Compared to phenol, which has 3 reactive sites, but in lignin only G or a non-condensed unit and the H unit has the reactive sites potentially for cross-linking, and also it also requires free phenolic hydroxyl groups specifically for phenol formaldehyde adhesive synthesis in alkaline conditions. So there are different ways to improve the lignin reactivities. The first one will be demethylation. Basically, it removes the methoxy and it turns the methoxy groups into hydroxyl groups, and it activates the other free sites in the benzene ring. And the other is hydroxymethylation. Basically, it use a lignin that react with formaldehyde first, and this method actually is not increasing the reactive size. It's just split the reaction happen for the phenol formaldehyde reaction. It's just split the one part reaction into 2 steps. React formaldehyde with lignin first. On the other hand, phenolation, this is a method that we think is the most promising because, as you can see from the graph, phenol can add on to lignin from different positions, and the add-on phenol will provide a more reactive size. It's very effective, especially using acid as a catalyst, and also another advantage is it can be integrated into the resin synthesis process, because we published this work in SAS Sustainable Chemistry 2 years ago, and we use only catalytic amount of acid, and this acid can be easily neutralized because in the resin synthesis we use obviously a lot of alkaline. This is not an issue, and potentially it can turn this modification and the resin synthesis into a one-part reaction. So in this research, basically we tested 2 different kinds of lignin. First is bio-choice lignin provided by Domtar. As I mentioned earlier, this is a pine craft lignin isolated by lignin boost process from craft mill, and the other is biorefinery lignin. And the lignin we used is actually is a sweet gum residue lignin. It's a hardwood, and it is isolated by ourselves using our own biorefinery process. The sweet gum wood chips first was treated by hydrothermal treatment, and then followed by mechanical refining. And after refining, we did enzymatic hydrolysis, and the leftover, the residue, is our second source of lignin. So as for the phenolation, we tested for both, in terms of improving reactivity. So for specifically for the reaction, we mix a lignin, phenol, and acid, let it react at certain temperature for 2 hours, and upon reaction completion, we add ethyl acetate to suspend the whole mixture, and then precipitate it into a petroleum ether. So the soluble part, which is a petroleum ether fraction, it contains the unreacted phenol, ethyl acetate, and petroleum ether, obviously, and the insoluble part is our phenolated lignin, and also the acid that we use also goes into this fraction. And afterwards, we wash with DI water to remove the acid, and giving us the phenolated lignin. For the BCl, because it's completely soluble, so we stop at there and dry before we use for adhesive synthesis. But on the other hand, for the biorefinery lignin, it's not 100% soluble. So we did a further extraction for research purpose. We extract the whole mixture with methanol acetone at a ratio of 1:6, which is a very good lignin solvent. And we further split the soluble and the insoluble fractions. And as I show in the left table, here, the optimum conditions for different kinds of these two different lignins is different. So for BCl, we need obviously the lignin to phenolation is a 3:5, but on the other hand, we need more phenol. So the optimum condition for biorefinery lignin is lignin to phenol ratio is 2:5, and also the yield. The total yield is also different. So for the biorefinery lignin, we can add on more phenol. So it gives the total phenol lignin yield is 145%. And also the after the phenolation, the solid, as I mentioned earlier, only 89% of the phenolated lignin is soluble, and we only use these 89% for adhesive synthesis. So these two tables tell us what has happened or what changes after phenolation. So let's look at the chemical composition first. So for the BCl pine craft lignin, it's original. The purity is very high. It contains 97% lignin, and after phenolation, actually the phenol become part of lignin. So the lignin content, we don't see like a significant decrease. They all condense back, so it's still like a 98% lignin content by the classical, the measurement of classic lignin plus acid soluble lignin, and this phenolated lignins are also like 100% soluble. And on the other hand, for the biorefinery lignin, originally only 82% are lignin. The rest are carbohydrates and other components we are not determined. And I want to point out that the polysaccharides here is only referring to glucose and xylose. There are other sugars are not reported in the polysaccharide side. Only about after phenolation, so the soluble part of the lignin content is 97%, and the insoluble part is very interesting. It's carbohydrate enriched, as you can see, about 50% carbohydrate, and this fraction was discarded and not used for further adhesive synthesis in this study. And For the molecular weight, it's quite obvious, like phenolation decrease the lignin's molecular weight. And here, for the SGS, which is a soluble fraction of the biorefinery lignin, only accounts for 30% of the SG, and it has a molecular weight of 6,600 daltons. The actual molecular weight for biorefinery lignin is perceptibly much higher. After phenolation, it drops to 3,000. This potentially will have some benefit of reducing the ratio viscosity. For the hydroxyl groups, we determined by phosphorus NMR, as you can see, I highlighted here. So the total reactive size was calculated based on the 5 free hydroxyl groups and also OH. So it's very obvious we improved or increased the reactive size significantly. And from the BCl, we increased from 2.7 millimoles per gram to 7.2. And for the biorefinery lignin, we increased like a lot more, from 0.5 to 6.3. So afterwards, we actually, there's 4 kinds of lignins: the original BCl, biorefinery lignin, and also the phenolated lignins, two phenolated lignins. We use these 4 to synthesize adhesive. The adhesive ratio was synthesized at 85 degrees Celsius, and the reaction time is 3 hours plus X. X depends on the viscosity we are looking for, so it will varies. The 2-stage synthesis, because we add the sodium hydroxide into 2 stages. So after adhesive synthesis, we apply those ratios in the yellow poplar panels at the 215 grams per square meter, and cured at 175 Celsius for 5 minutes. The pressure was 0.86 megapascal, which is equivalent to 125 psi. And after curing, we placed the panel in the conditioning room. Let it like conditioned at 23 degrees Celsius, 50% humidity for 7 days. After 7 days, we took it out and cut into 14 spacemen, and then tested the shear strength according to the industrial standard ASTM D906 standard. So this is the example of the pure phenylformaldehyde adhesive formula. So we kept the formaldehyde to phenol at 1.9 to 1 mole to mole ratio, and we kept the final ratio at the solid content of at 50%. When lignin was used, we adjust for the phenol part, we use the same formaldehyde to phenol ratio 1.9 to 2, and for the lignin side, we use the reactive size determined or calculated from the phosphorus NMR result, and kept a formaldehyde to phenol ratio at 1 to 1. So this is the final the strengths. So let's for the pine craft lignin, as you can see from here, without phenolation, which is a blue bar here. So we can replace phenol by 35% without significantly sacrifice the adhesive strength. But when it goes to 45%, we see, like obviously the strength decrease. After phenolation, we can definitely increase the phenol replacement level up to 45%. But on the other hand, for the biorefinery lignin, it's very interesting. So up to 35% without phenolation, the adhesive showed almost identical performance. We cannot go up to 45% because it is almost like a solid mud we cannot apply the adhesive. So that's why there's no data on the 45% replacement level for biorefinery lignin. But after phenolation, this is very important and very interesting. After phenolation, the actual performance of adhesive decrease. This is not of our what we expected. So we don't have any proof yet. We are working on that, but there's some possible reasons why the biorefinery lignin behave so much better even without phenolation, and actual phenolation is decreasing its performance. So the first possible reason is the residual polysaccharides. As I mentioned earlier, there's only 80% and in lignin in the biorefinery residue, and these residual polysaccharides could provide extra hydrogen bonding. And this is the evidence here is the research done by USDA in 1985. Actually, they figured if you hot press 2 panels, only use concentrated sodium hydroxide solution, you can get a very good dry bonding strength. Obviously, these alkaline activates, potentially, cause the polysaccharide swelling and also provide more bondings by carbohydrate. And another evidence is lignin structure. So we characterize the lignin structure change through the biorefinery process. This result was published recently in Chemsys Chem, and we figured the beta-04 in the sweet gum, this biorefinery residue lignin, they are almost like 25% per 100 C9 left. And another research was done by Dr. Yella. I'm not sure I'm pronouncing the name correctly or not, but they figured the phenol formaldehyde, pure phenol formaldehyde could condense with lignin through methylene bridges, and also the curing process caused the degradation in the wood cells of lignin. So the reaction will be very similar to the a reaction happen in pulping. We have a degradation of original native lignin structure and also condensation in the alkaline condition as well. So we are working on these speculations, and hopefully we'll figure out, get more evidence. So as a conclusion, for the phenolation, it can successfully increase the reactive size in lignin and decrease lignin's molecular weight. And for the pine craft lignin, we can replace 25% phenol without phenolation and without sacrificing adhesive strength. With phenolation, we can improve the replacement level up to 45%. On the other hand, for the biorefinery lignin, we can replace 35% phenol with almost identical adhesive strength, but phenolation did not improve the phenol replacement level. So that's all for my presentation, and thank you for your attention, and I'd like to take some questions. Thank you.
Okay, thank you for your presentation. So now open to discussion and questions. Do you have any questions? If you don't have any question, I will make short question. Is it okay?
Sure.
Or just I ask about back to the number of reaction site of phenol and glyacol type.
Okay.
I'm sorry, not the constant actually. Yeah, this one. You check 3 position of phenol and 1 position G, 2 position H, right?
Yes, that's the theoretical position.
Yeah, but you write also non-phenolic type, not only phenolic type. So I think not only this position, but also other position can work, no? Because methoxy group exists. For example,
you are referring the 6 positions.
yeah, something like
right?
that. Yeah, something
Okay.
like that.
So it is possible, but right now we, I mean, honestly, I don't have evidence. And based on the reaction condition for the pure phenol formaldehyde synthesis, the reaction starts with the deprotonation of free phenolic groups, and I'm talking about for phenol. So the alkaline deprotonate this and further activate these 2 ortho and 1 para positions. Potentially, this oxygen in mesoxy groups could activate 6 positions. This is also another researcher in our group. He's trying to find evidence whether this is going to react for the manic reactions. But so far, we do not, based on his results, it's also like a react with amine and formaldehyde. Based on his results, we currently do not have evidence the phenol will react at 6. But if you are increasing the temperature for example, the curing condition, much higher temperature, it could.
Okay. Okay. Thank you. Do you have any questions, others? Okay, already time is coming. Thank you again.
Thank you. Thank you so much.
So now this session is over. So please check your chat. The office wrote some information about tomorrow. I read it. Please note that session 4, 5, 6 or 9 tomorrow are held by a different Zoom webinar URL from today. And session 4 starts at 9 a.m. on 9th, Tokyo. And this is USU Eastern Time, 8 p.m. on 8th. Okay, today for USA and Canada. And there, that is today, actually. So thank you very much. Please, Oi-sensei.
Yes, thank you very much, all of friends, participants, and chairperson. Today, shall we close today's session and see you tomorrow early in the morning for Japanese.
Okay, thank you.
11 p.m. in Japan.
See you.
But I like to see all of your attendance face. So internet conference, no communication, face to face. Okay, so maybe I like to take a screenshot for 1 day, for past days. Okay. Any other persons? Coming. Now, 1, 2, 3, 4, 5, only 20. 25. One more. Akira Isogai, please. Oh, yes. Okay. Pyong. Maybe I took. Okay. Any others? Okay, good night. Okay, go next page. Oh, next page. Oh, next page.
Okay, totally we have 53 people, okay?
Yes. So this evening session, we have much more than afternoon session, the rest of afternoon session. Indonesia now, 9 p.m. And Taiwan and Japan is the same time. Matsumoto sensei, 3P. Okay. Wow. Matsumoto sensei now in the office.
No, I'm
putting
at home.
Necktie, right? Necktie.
Yeah, to show my full respect to Oi-sensei.
Today, Professor Fateh is so fine, so active. But Japanese audience so tired. We are very sorry.
It's your late evening. Here we are. It's early
And
morning,
no
so
banquet,
that's
no
that's why.
banquet. Yes, no banquet international conference, internet conference. We have no banquet.
Give me some drink.
Yes, how can we improve?
Free drink.
So actually, 2 years later, we have a plan to the next international panpac conference,
Again in Tsukuba?
probably in Indonesia.
Okay.
But maybe in Indonesia, we don't have beer, no beer. But maybe not dancing and singing, right?
We
Singing
have
and
coffee.
yes. Oh, yeah. Why you are watching me? So many people.
Because your face is here.
please see to each other like that.
I don't know how we can do that.
Wow. Chat. Who chatted?
Okay.
You learn how to chat or how to raise your hand in the international conference? No? Yes? Oh. Does anyone take photos? I'm not familiar with taking photos.
Well, thank you, everybody. Harash and see many of old
hey.
friends.
Everybody.
Yeah, thank you.
Yes, you must work today hard. So,
Yeah, well, your late afternoon session, we are not able to join because it's in the second half of the night. So in the morning session, some of us could join. Okay, thank you very much, Professor
Yes,
Oy, for
thank you very much.
your organization. Yeah, okay. Enjoy, have a good, sweet dream. Okay, I'll see you tonight, our time. Bye-bye.
Goodbye.
Bye-bye.
Thank you very much, all. Thank you. Bye-bye.
See you. Thank you. Bye.